औज़ु बिल्लाहि मिनश्शैतानिर रजीम बिस्मिल्लाहिर रहमानिर रहीम रब्बि इश्रह ली सदरी व यस्सिर ली अमरी वहलुल उक़दतम मिन लिसानी यफ़क़हू क़ौली। Section 10 Introduction to Welding Processes. 10.1 General Common Characteristics of four main arc welding processes: MMA, TIG, MIG, MAG and SAWR. An arc is created when an electrical discharge occurs across the gap between the electrode and parent metal. The discharge causes a spark to form, causing the surrounding gas to ionize. The ionized gas enables a current to flow across the gap between the electrode and the base metal, thereby creating an arc. The arc generates heat for fusion of the base metal. With the exception of TIG welding, the heat generated by the arc also causes an electrode surface to melt, and molten droplets can transfer to the weld pool to form a weld bead or run. Heat input to fusion zone depends on the voltage, arc current and welding or travel speed. 10.2 Productivity. The most welding processes welding in a PA flat or 1G position result in a highest weld metal deposition rate and thereby productivity. For consumable electrodes welding processes, the rate of transfer of molten metal to the weld pool is directly related to the welding current density ratio of the current to the diameter of the electrode. For TIG welding, the higher the current, the more energy there is for fusion, so the higher the rate at which filler wire can be added to the weld pool. 10.3 Heat input. Arc energy is the amount of heat generated in the welding arc per unit length of the weld and is usually expressed in kilojoules per millimeter length of the weld. Heat input for arc welding is calculated from the following formula: arc energy kJ over mm, kilojoule over per millimeter, is equal to volts into ampere over travel speed into 1000. Heat input is the energy supplied by the welding arc to the workpiece and is expressed in terms of arc energy into the thermal efficiency factor. The thermal efficiency factor is the ratio of heat energy into the welding arc to the electrical energy consumed by the arc. Heat input values into the weld for various processes can be calculated from the arc energy by multiplying the following thermal efficiency factors: SAW wire electrode 1, MMA covered electrode 0.8, MIG mag 0.8, FCAW with or without gas shield 0.8, TIG 0.6, plasma 0.6. Example: a weld is made using the MAG welding process and the following welding conditions are recorded: volts 24, ampere 240, travel speed 300 mm per minute. Arc energy is equal to volt into ampere over travel speed millimeter per second into 1000 is equal to 24 into 240 over 300 over 60 into 1000, 5760 over 5000. Arc energy is equal to 1.152 or 1.2 kilojoule per millimeter. Heat input is equal to 1.2 into 0.8 is equal to 0.96 kilojoule per millimeter. Heat input is mainly influenced by the travel speed, welding position and the process have a major influence on the travel speed that can be used. For manual and semi-automatic welding, the following are general principles. Vertical up progression tends to give the highest heat input because there is a need to weave to get a suitable profile, and the Forward travel speed is relatively slow. Dot. Vertical down welding tends to give the lowest heat input because of the fast travel speed that can be used. Dot. Horizontal vertical welding is a relatively low heat input welding position because the welder cannot weave in this position. Dot. Overhead welding tends to give low heat input because of the need to use low current and relatively fast travel speed. Dot. Welding in a flat position downhand can be a slow or high heat input position because the welder has more flexibility about the travel speed that can be used. Dot. Of the arc welding process, SAW has the potential to give the highest heat input and deposition rates, and TIG and MIG-MAG can produce very low heat input. Dot. Typical heat input values for controlled heat input welding will tend to 1 to 3.5 kJ per millimeter. 10.4 Welding parameters. Arc voltage. Arc voltage is related to the arc length for processes where the arc voltage is controlled by the power source SAW, MIG, MAG or FCAW and can be varied independently from the current. The voltage setting will affect the profile of the weld. As welding current is raised, the voltage also needs to be raised to spread the weld metal and produce a wider and flatter deposit. For MIG-MAG, arc voltage has a major influence on droplet transfer across the arc. Welding current. Welding current has a major influence on the depth of fusion penetration into the base metal and adjacent weld runs. As a rule, the higher the current, the greater the penetration depth. Penetration depth affects dilution of the weld deposit by the parent metal, and it is particularly important to control this when dissimilar metals are joined. Polarity. Polarity determines whether most of the arc energy heat is concentrated at the electrode surface or at the surface of the parent material. The location of heat with respect to polarity is not the same for all processes, and the effects, options, benefits for each of the main arc welding processes are summarized below. Process MMA. DC positive polarity, best penetration. DC negative polarity, less penetration but higher deposition rate, used for root passes and weld overlay. AC polarity, not used for some electrodes, minimizes arc blow. Process TIG. DC positive, rarely used due to tungsten overheating. DC negative, used for all metals except aluminum and aluminum alloys and magnesium alloys. AC polarity, required for aluminum and aluminum alloys to break up the refractory oxide film. Process GMAW solid wires, MIG-MAG. DC positive, used for all metals and virtually all situations. DC negative, rarely used. AC not used. Process FCAW or MCAW, gas shielded and self shielded core wires. Positive, DC positive, most common. DC negative, some positional basic fluxes wires are designed to run on negative. Some metal cord wires may also be used on negative polarity, particularly for positional welding. AC not used. Process SAW, DC positive, best penetration, DC negative, less penetration but high deposition rate, used for root passes and overlaying. AC used to avoid arc blow, particularly for multi-run electrode systems. 10.5 Power source characteristics. To strike an arc, a relatively high voltage is required to generate a spark between the electrode and base metal. This is known as the open circuit voltage OCV and is typically 50 to 90 volt. Once an arc has been struck and stabilized, there is a relationship between the arc voltage and current flowing through the welding circuit that depends on the electrical characteristics of the power source. The relationship is known as the power source static characteristics, and power sources are manufactured to give a constant current or voltage characteristic. 10.5.1 Constant current power source. This is preferred type of power source for manual welding MMA and manual TIG. The volt ampere relationship for a constant current power source is shown in figure 10.1 and shows the no current position, the open circuit voltage, and from this point there are arc voltage or current curves that depend on power source for the various current settings. Figure 10.1 Typical volt ampere curves for a constant current power source. For manual welding MMA and manual TIG, the welder sets the required current on the power source, but arc voltage is controlled by arc length the welder chooses. A welder has to work within a fairly narrow range of arc length for a particular current setting. If it is too long, the arc will extinguish. Too short, and electrode may stub into the weld pool and the arc extinguish. For the operating principle of this type of power source, see figure 10.1. The welder tries to hold fairly constant arc length B in figure 10.1 for the current Y that has been set. However, he cannot keep the arc length constant and it will vary over a small working range A to C due to the normal hand movement during welding. The power source is designed to ensure that these small changes in arc voltage during normal welding will give only small changes in current X to Z. Thus, the current can be considered to be essentially constant, and this ensures that welder is able to maintain control of fusion. The drooping shape of the volt ampere curves has led to constant power sources sometimes being said to have a drooping characteristic. 10.5.2 Constant voltage power source. This is the preferred type of power source for welding process that have a fire feeder, MIG, MAG, FCW and SAW. Wire feed speed and current are directly related, so that the current increases, so does the feed speed, and there is corresponding increase in burn-off rate to maintain the arc length or voltage. The operating principle of this type of power source is shown in figure 10.2. A welder sets voltage B and current Y on the power source. If the arc length is decreased to C due to variation in the weld profile or as the welder's hand moves up and down during the semi-automatic welding, there will be a momentary increase in welding current to Z. The higher Z gives the higher burn-off rate, which brings the arc length and arc voltage back to the preset value. Similarly, if the arc length increases, the current quickly falls to X and the burn-off rate is reduced, so that the arc length is brought back to the preset level P. Thus, although the arc voltage does vary a little during welding, the changes in current that restore the voltage to the preset value happen extremely quickly so that the voltage can be considered constant. The straight line relationship between voltage and current and the relatively small gradient is why this type of power source is often referred to as having a flat characteristic. Figure 10.2 typical volt ampere curves for a constant voltage power source.